In Chapter 3, we're going to be doing pretty much all of the sections, and in fact all of them. So we'll start off with function, and then later graphs and function, applications, quadratic, polynomial, and then later rational functions. And we'll move on to topic 1, which is functions. Now, we did look at functions a little bit already, in fact, function notation, and they will introduce us to that as we go to example 1. The amount of electric bill you pay depends on the amount of kilowatt hours. The way in which usage determines the bill is given by the rate per kilowatt hour. In example 2, we're looking at a relationship of, along this end, percent, that's your y-axis, and then time along the x-axis. And these blue bands indicate recessions of some type. And then the poverty rate is our line graph. And we can make some observations about it, but let's see what they're asking us. And so far, just observations. In physical science, suppose a rock is dropped straight down from a high point. What is the distance traveled by the rock in t seconds if the rate is 16 t squared feet per second? So in all of these, this is what they're bringing in now, there is all the usage of kilowatt hours, all of the people per year in poverty, and then the seconds that elapse since dropping the rock. So this will be our input information. Our output is the amount of the bill, what the poverty rate is, and of course the distance the rock travels. Now these are the rules. This was the input information, this is the output, and this is the rule that governs it. So in a sense, I don't know if you can see it here, but I think it's quite obvious that when we were doing y equals mx plus b, it depended on what value we had for the x and these others, the slope and the y-intercept, as to what value the y would have. So the x here was the input into this formula, and then our output was y. And as we mentioned earlier, I believe, we could substitute for y a function symbol. So this is what we're building up. 2. A function consists of a set of inputs called the domain, which was our x value, and a set of outputs called the range, which is our y value. So we're building up to this concept of function. So in example 4, find the domain and the range for the functions in examples 1 and 2. Well, let's look at what we have. So if we put it in sort of a function notation, our x's were the number of hours that we used, and this was the price per hour. So the domain was the number of hours that we would have used, and then the price would have been our range. This is what they're saying here. In example 2, the domain is a set of years from 1959 to 2011, all real numbers in that interval, and the range consists of the poverty rate that actually occurred during those years. Now, in a function, the x element is only used once. And this is what they're sort of saying here. I like it this way. If the x element is only used once, then what you have is a function. Now, which of the following rules describe then a function? Use the optical reader at a checkout counter of a supermarket to convert codes to prices. Well, will that barcode only produce one price? Yes. So this is a function. Now enter a number in a calculator and press the x squared key. Will that just produce one function? So you say 3, and then you hit the x squared key, that's going to produce 9. So that produces one function. So this is a function. Now, as we look at our ordered pairs here, x comma y, these are our domain elements. These are our x values. Now here, x is producing a 1 is producing a 3. The 1 is also producing a negative 3. So the x element is used more than once. So this is not a function. Okay? I like my definition here. In letter D, we have this value, which is y equals 3x minus 5. And we said to do these, normally we put various values for x here. Now, if we have a value for x, that particular value for x, if it's only used once, is going to produce a particular value for y. So the x element in this function would only be used once. So this does define a function. All right, let's go on to 6. So again, this is in slope-intercept form, and this one happens to be negative slope. Does this negative slope define a function? Well, the x value for something like this is only used once. So this defines a function. Now, an interesting way to see this is if we were to make a graph of this, the graph of this looks like this. It's kind of a sideward parabola. Now notice this point up here has a value of, let's say, 2 for x, and this point down here has that same value for 2. So in a sense, x is used twice for all of these. Therefore, when you have y squared equals x, this is not a function. Now, an interesting aside, and I think they might ask for this later, but how about if you have y equals x squared? Now, this defines a parabola that looks like so. Now here, your x values for this parabola are only used once. So if you have x squared, this defines a function. If you have y squared, this does not define a function. And later we're going to give you another easier rule to follow too. Now for some of these, we're going to give you definitions. And for y equals various powers of x, the graph of this, I think, looks sort of like that. And again, the x values here in this graph are only used once. So this defines a function. And the domain of this function, since this eventually goes off to negative infinity in this direction for our x values, and off in this direction to positive infinity for our plus values, and these are values of x. This is a function, and interval notation for it would be written as this, which are all real numbers. Now, looking at letter B, we want to find what is our domain of this. Well, we had mentioned you can't have, under a radical sign, a negative value. These are not real numbers. So the lowest value we can have under a radical sign is 0. So we solve this by equating what the radicand is. X minus 6 is greater than or equal to 0. When we solve that, we get x is greater or equal to 6. So our interval notation is, it would start and include 6 and go to positive infinity. And as a little quick review, the graph of this, you might recall, is going to start here at 6, and it looks like so. Now for letter C, again, what's under the radical sign has to be greater or equal to 0. Now a quick way to solve this, just take the negative x, put it to this side, and you get 4 is greater or equal to x. Or you can read it this way, x is less than or equal to 4. Now in this case, when you look at it, you might say, well, wait a minute. If you made a graph of this, it would be at 4, but it would be a bracket, and then you would fill it in this way. And you might say, how could it have all those negative values where we're not allowed to have negative under the radical sign? Well, because our x itself is a negative of x. Now, if we put, for instance, a negative 4 there, this will be x negative times a negative 4 makes it a positive 4. So that's where this mystery can be explained, that all these negative values make this x positive. Now, if we tried to put let's say a 6 in there, that would be 4 minus 6. This would then be the square root of negative 2, and you can't have that. But any negative value, and then of course up to 4. If you put a 4 there, it's going to be 4 minus 4 is 0, and that's okay. So your interval notation is from negative infinity up to and including 4. Now for this one, and I'll clear that up, we can't have any value that makes our denominator a 0. So if we equate our denominator to 0, we get x plus 3 equals 0, x equals a negative 3. If we were to put a negative 3 there, that would make our denominator a 0. So because of this then, we say that our domain can be any real number, but x cannot be a negative 3. That's what they're showing. It could be any other number, but it cannot be negative 3. And in interval notation, it would look like this. And instead of the or, we sometimes see the union symbol there. That it stops just before a negative 3, picks up right after a negative 3. Now, letter E, we have two things going on. Here in our numerator, where x could be 0, but it cannot be any negative number. And then when we equate our denominator to 0 and factor it, we get these values that our denominator, having this as x is a 1 or x is a 2, would make our denominator 0. So this is going to be all non-negative real numbers, that is, starting with 0, so all non-negative numbers can't have that. And then you cannot have a 1 or a 2, and that's what they're showing here. All right, we're now going to move into what is called functional notation, where we have this symbol, which is read f of x, or the function of x. And let's look at some examples. So here now, instead of using the letter y, as we've done so often, we are replacing the y with the function symbol. So all of these could be function of x as well, converting these to function notation. And what does that mean? Well, we find what x value we're going to use, replace it here, square it, and then add 1, then take the square root of it. So our input will be an x value, and our output, once it goes in here through this machine, in a sense, gives us our y output. So they're giving us various examples here now where we put for our x value a 3. So we would put a 3 in there. 3 squared is 9. 9 plus 1 is 10, the square root of 10, and that's what they're showing. If we put a negative 5 in there, again, we do the substitution, we do the math, and we get various values. Now, sometimes instead of just being an x as 3, they're going to say our x is a plus b. So we put that where the x would have been, expand that, and do it this way, as they show with this example here as well. Whatever they put after the f, the function, in our x spot, that's what we replace in the machine, in the sense. This is our little calculator that we're going to work. Now we jump from the somewhat easy to the more challenging. So here they're saying the function g of x, we could use other letters, equals a negative x squared plus 4x minus 5. So we're looking for what value do we replace the x with. Well, here in letter A, it's going to be a negative 2. And they've worked that through, and we end up with a 17. Now here it's going to be this x plus h. And again, we carefully put that in there. This is going to be time consuming. We're going to use that method to square a binomial. We get this. We're going to distribute this one to get that. We're now going to remove this parenthesis by changing all the signs. And then we collect like terms. Wow. Now another type of function you might get is where you have this, and again this in particular for our first g, and then we're going to subtract everything and put an x in the other function. So substituting here, we're putting this where the original x was up here and expanding that, and then keeping in mind now this is in one big parenthesis, and we can just remove that parenthesis, but now we're going to subtract this, which is just our single x here, and we put that in parentheses, and then when we subtract it, all of these change their sign. This becomes a negative, this becomes a positive. And then now just remove that parenthesis, and all of these now start canceling out and combining like terms. This will cancel out here. And do we have a 4x there? Yes, minus 4x with this. So now we're just left with this one, and this one, and it gives you this one. Wow. Lots of stuff going on. They started us off easy, but now it's very challenging. Well, if we look at letter C then, we've done this and we get this, but lots of work. They're now asking us for letter D now, where we're going to divide this, which is this, by H. So notice there is an H in each of these terms that we're going to factor out. And then we divide the H out there, and we're left with this. Wow. So for something like this, remember you're going to do it carefully and meticulously and item by item, and hopefully you end up with the right answer. Going on to those who go on to calculus, you'll be doing stuff like this. All right, let's go on to applications now. Example 9. If you were a single person in Connecticut, which we are, many of you, not me, 2013, with a taxable income of X dollars, and your earning was less than $500,000 to $500,000, then your state income tax was determined by this rule. So you had this and this, sort of that piecewise function that we spoke of earlier. And they're giving this qualification and then this qualification. So it's sort of in two parts. So in part A, since you were less than 10,000, you do this part of the formula, take 3% of this amount, and you get your state income tax was $276. Now for 30,000, let's look at this in some detail. Now you're going to pay 3% of the 10,000, which is $300, and then you're going to pay 5% of what was left, which is 20,000, and your overall tax then is $1,300. Again, we did this earlier in piecewise defined functions. And in example 10, suppose the projected sale in thousands of dollars of a small company over 10 years are approximated by this function. What are the projected sales for the current year? Well, X would then be 0. So all of these would be 0, and therefore it's just $62 or 62,000, since this is in thousands. Now when you increase your value or time in terms of 4 years, you're going to put now where X is listed a 4 there. Carefully do all of this, and you end up with 136,470. And again, depending on the calculator you're using, you can put all of this in and get results. Okay, and then here, use the table feature of the graphing calculator to find the projected sales of a company in example 10. Well, again, this would be something esoteric if you're using a graphing calculator. And we're going to say for 5 years. And we end up with this. So the company's doing well, and looks like the sales are increasing. All right, this winds up topic 3.1.